My name is Jay Lago. I'm a fourth-year student in the Computational Science Joint Doctoral Program. My advisors are Dr. Chris Curtis and Dr. Alex Eiler. And this is a method that we've developed called Deep Learning Dynamic Mode Decomposition, or DLDMD. And our work is sponsored by the Naval Information Warfare Center here in San Diego, as well as the Office of Naval Research. So our method is underpinned by something called the Koopman operator. Now, to understand the Koopman operator, if we think for a moment about just general dynamical systems, something of the form dx dt equals f of x, where f is just some function, could be nonlinear. The Koopman operator describes the time evolution of what are known as observables of this system along its affiliated flow. And we write this as k acting on g of x, where g of x are the observables and k is the Koopman operator. So because k is acting on functions, these g of x's, it's an infinite dimensional operator. However, we can show down below that it's also a linear operator. And because of that, we can identify spectral pairs, so eigenvalues and eigenfunctions, from which we get decompositions of our data, as well as building out full time-stepping models using those eigenfunctions and eigenvalues. So this Koopman operator captures the time evolution of these observables for any dynamical system, including nonlinear ones. The question then that we should ask ourselves is, can we identify finite dimensional approximations of this Koopman operator? And the answer to that, in some sense, is yes, as demonstrated by Peter Schmidt back in 2010. A straightforward data-driven approach to Koopman analysis is something called dynamic mode decomposition. Now, it turns out that DMD is highly dependent on this choice of observables, these functions of the data that you use in order to obtain your fits in the dynamic mode decomposition. What we've done is incorporate deep learning models to choose those observables for us. And we see this in sort of a diagrammatic form where we have our data that we've recorded of our system in red up above. So these are the original nonlinear dynamics evolving according to this unknown function f. And we train an encoder neural network E and a decoder neural network D that allow us to move back and forth between these original nonlinear coordinates and these latent linear coordinates in green. And we represent the latent dynamics simply by a linear operator, k, that takes us from time step to time step. So in some sense, we've circumvented the nonlinear dynamics via Koopman by choosing the optimal set of observables using these neural networks. To see the results of this, if we look at a simple nonlinear system, here the Duffing oscillator, this is a two-dimensional system where we see its phase coordinates, the trajectories in its phase coordinates mapped out here on the left, and its affiliated latent coordinates through DLDMD mapped out on the right. The two things to note are, one, we've actually allowed our encoder network to embed these trajectories, these nonlinear trajectories, in a higher dimensional space, latent space. So we go from 2 dimensions in our phase coordinates to 3 dimensions in our latent coordinates. More importantly, what we see is in the latent coordinates that all of the sort of nonlinearities have been kind of smoothed out. So we have these roughly linear sort of periodic orbits in the latent coordinates. So to learn more about the underlying method itself, come see me in my poster, and I'll be happy to talk about it. Thank you.